Good day, everybody. I welcome you to the course, namely Digital Voice and Picture Coding. As the name indicates, so this course concerns the coding of digital or digital coding of voice and picture signals. At some places, it is this course, I mean at some institutions, education institutions, this course has different titles like digital voice and picture communication, digital voice and picture compression, and similarly a few other variations are there. The content of these various courses have a lot of common part, and hence although the name of the course is digital voice and picture coding, so this can also be considered as voice and picture communication and voice and picture compression. The coding of signals like voice, audio and video is used for both or are used for transmission purposes as well as for storage purposes. Strictly speaking, the transmission applications are more wide based, and it is applied in offering systems offering different communication services. So let me start by defining the services and then the application of signal coding in services, and then continue my discussion. So let me discuss about the course in general or introduce the course. By considering the transmission and storage applications. So in a transmission application, typically we take the signal from a signal source which is located at one end and then communicate it over a medium, a communication medium, to a destination. Well, for this purpose we use a transmitter at the source end, and we use a receiver at the receiving end. Now in doing so, we have to do coding or apply coding on the signal so that the signal is compressed and occupies a smaller bandwidth of the transmission medium. Very often this is needed to multiplex a large number of signals onto a fixed communication medium and transmit it to the receiving end. Now the communication is very essential to offer different services to the users, and the services can be classified in different forms, but here I'll classify it based on the kind of signals it uses. So telephone services are very widely used by a very large number of users world over, and it is known to many of you. So the telephone service uses speech transmission from one end to the other end. Then video services wherein the picture signals are transmitted from one end to the other end, and there are different variations of these services that are offered. It can be a picture phone application wherein a picture is transmitted along with the speech to the destination. Then it can be a conferencing application where we transmit the picture also along with the speech, and then if the number of users are more than 2, it becomes a conference, and then we have picture transmission there. Then we have information services. Where we use the speech, picture, and also data. So let me first define data services separately and then come back to the information services. We have several data sources like computers, where we transmit a file from one computer to another computer, and the graphics information from one computer to the another information, text from one computer to another computer, and we have fax also as a data service. So therefore we have basically data transfer like the file transfer, or it can be text or data, and it can be graphics, and it can be fax data services. And then information services include all these media: voice, picture, and data, and they offer transmission of all these media over networks. So this is as far as the transmission is concerned. Similarly, so this is applied for the coding techniques are applied for storage purposes also, to conserve the storage media. As you have seen, in all these systems, in all the systems which offer these services, we have different kinds of sources, signal sources that are present, and the signal sources are speech sources, which produce speech signals, and it can be audio, that means music signals. Then we have video producing picture signals, and we have data. Let me first define a little more or describe these signals a little more. Speech has two types of signals. It is normal telephone quality speech signal, which is band limited to about 3.4 kilohertz. Typically, not the audible spectrum of speech has a band ranging from about 16 hertz to 20 kilohertz. Out of this entire band, to save the bandwidth of the signal is limited to 300 to 3.4 kilohertz, and there are also a few variations of these, and then it's transmitted to the destination. Because of this band limitation, the quality is not equal to that of a music signal. The quality is slightly poorer than that of a music signal, but it is good enough for telephone conversation. So such signals are telephone signals. And we have wideband speech, which is also used in certain applications where the bandwidth is not limited to just 3.4 or 3 to 3.4 kilohertz, but the bandwidth is limited to about 7 kilohertz. Hence the quality of the wideband speech is better. So this is mainly used for speech distribution. Then audio signals are music signals, as I explained. So the bandwidth of an audio signal may vary between 20 hertz to 20 kilohertz. And there are different qualities of audio that is used. For broadcasting purposes, the audio signals are band limited to 5 kilohertz, and in some applications they are band limited to 10 kilohertz, and in some other applications like high quality music signals like CDs use up to 20 kilohertz. The video signals are monochromatic video signals and color video signals. We have the video signals used in different applications, and we have video signals used in surveillance applications, conferencing applications, and broadcasting applications, and then some storage applications like CD applications. And depending on the quality that is required, the video frame rate and whether it is color or monochromatic is decided, and the signals are standardized. So as I mentioned, the data services or the data source includes either binary data or it is in the form of characters. In fact, one can be converted into another form. Hence, it is data which is in some binary pattern like ones and zeros or in some ASCII character form. Now let me discuss about the signals in detail, or the how to convert the signals into digital form, and then continue discussing about the introduction further. So here, digital speech. As I mentioned earlier, the speech is first band limited by a band pass filter or a low pass filter to about 3.4 kilohertz typically. Then the signal is sampled to make it into a discrete form. Then it is analog to digital converted to quantize the samples to discrete quantum levels and code it into a binary form. So what we have here is a digital signal, whereas the original signal is an analog form. Because all these sources which we discussed about, out of these sources, the speech, audio, and video are an analog form to start with, whereas the data is a digital signal as it is. Since the signals are in analog form, they have to be converted into digital form in order to achieve, or in order to have some advantages, or in order to have digital processing for compression purposes and digital form of transmissions and digital form of storage. So basically, the signal is an analog signal here at the beginning. Now this signal is first, as I mentioned, is a time waveform, and the signal is either a voltage signal or a current signal. Now this signal is sampled at regular intervals, the interval being the sampling time, and typically for telephone quality speech, the sampling frequency is 8 kilo samples per second, because the Nyquist rate for 3.4 kilohertz is 6.8, and the sampling rate has to be higher than more than 8 kilo samples per second. Hence 8 kilo samples per second is taken as the standard. Now once the signal is sampled, you have this signal, sampled analog signal. Then the sampled analog signal is analog to digital converted by the A to D converter here after sampling. And here after sampling, now the signal becomes an analog signal but discrete, x0, that means t equal to 0, and at xt at t equal to ts, that is this sample, then x at t equal to 2ts, and so on. Now, an analog to digital converter converts these analog samples into a digital form, and after the analog to digital converter, what we have is a discrete signal, a digital signal. So x0 is a number which represents the first sample, and x1 is the number which represents the second sample, that x at t equal to ts, and the third one is x2, that means that is a number which is a close approximation to x at t equal to 2ts, as a rounded off version of the xt at t equal to 2ts conversion. Therefore, a digital signal is a signal which is a series of numbers. Now, this can be used to store in a storage medium, and these can be used for transmission purposes. So, a continuous time waveform is converted into a sequence of numbers. Similarly, audio signal is also converted. Audio signals are also converted into digital form, where the difference between the speech and audio signal says in terms of the bandwidth, the sampling rates, and the accuracy of the A to D conversion, and so on. Yeah, mainly these are the differences. Now, digital video. Picture is basically a three-dimensional picture. If you look at my picture, at any instant of time, it is a two-dimensional picture distributed in the x and y directions. Now, this picture is not constant with respect to time. It is changing from time to time. Hence, it's a spatial distribution of the intensities and color. But this spatial distribution, two-dimensional spatial distribution, is varying with respect to time, because there is time variation. Hence, the picture is a three-dimensional signal, with the variables being x, y, and the time. Intensity and color vary according to x, y, and time t. Now, what we do is, like in the conventional TV, the signal is first sampled in time. That means snapshots are taken for the picture, for the time varying picture, at the rate of say 25, 30 frames per second, or at a lower level depending on the kind of application and the quality required. So, what you have is now, because of the sampling and time, what you have is fixed snapshots. So, pictures like this. So, this is first picture. So, this is next picture, and so on. We have a series of photographs or pictures or images. Whereas this is a progression in time. There is the first snapshot, there is the second snapshot, and so on. Therefore, now we have a set of two-dimensional pictures because of sampling and time domain. Now, further, this spatial picture, which has spatial coordinates x and y, is sampled in the spatial x direction. So, like this. And in the spatial y direction. And then each one, at each of this small area, the average intensity is measured, and that average intensity is the sample picture. Now, once this is sampled in this form, so at the center of this picture location and at the center of picture location and the center of this picture location, the intensity is measured. So this intensity is x at say delta x, x at or the intensity at 0, 0. And the next intensity is the intensity at the location delta x and y equal to 0. So assuming that this is 0, this is the 0, 0 point. So the next one will be the intensity at 2 delta x, and along the y direction it is 0 delta y. The next row would be therefore at this is at y equal to delta y and 0. So this is the intensity. This intensity is at I equal to delta x and delta y, and so on. Now the sampled picture, sample in a picture which is already a sample version of a time varying picture, is now further sampled in x and y directions, and it is still analog with these intensities given in analog form, but they are discrete in the x direction and in the y direction. Now these samples, analog samples, are then digital converted, and the digital equivalent corresponding to the analog intensities is obtained. So when you replace these analog intensities by their corresponding number equivalent, the signal now becomes a matrix. The picture signal therefore is a matrix, and the size of the matrix depends on the number of rows and columns we have there. That means the number of samples we have in the x and y directions, which naturally depends on the quality requirement. And each one represents the intensity of that picture element at that location 0, 0. Therefore, these are all the various pixel intensities digitized. Although it is a two-dimensional picture, we can convert it into a serial form by first taking this pixel, next this pixel, and so on, covering the first row, and then taking this pixel and this pixel and so on, covering the next row, and so on up to the last row, and we can convert it into a single sequence of numbers. And so on, and we can make it into a one-dimensional digital signal. So please note that what I have now discussed about is one snapshot or one picture or one image. Now since the signal has several pictures in it, so what we do is this is first converted into a matrix, then this is converted into another matrix, and so on, in which case it's a two-dimensional sequence of two-dimensional pictures, and then our sequence of two-dimensional matrices, and they can further be converted into a one-dimensional sequence by first converting it into a one-dimensional sequence, converting the first picture into a one-dimensional sequence, then converting the next picture into a one-dimensional sequence, and then transmitted one after another, and continuing further, you have the sequence coming like this. This is for the first picture, comma, then the sequence for the next picture, and then the sequence for the next picture, and so on. It becomes a one-dimensional sequence. Now the typical sizes are which are used for the image processing applications are like 256 by 256 and 512 by 512, whereas for communication and storage purposes we use NTSA and PAL formats, and for storage purposes we use QCIF format and so on, and these will be discussed at length in the subsequent lectures. Therefore, the size of the picture would be say like of the order of 512 by 512 or 256 by 256. Well, in case it is 512 by 512, the number of picture elements therefore are half k into half k is about 1/4 of mega samples. Now, if these 1/4 mega samples per picture are converted to 8-bit numbers, then each sample is converted to an 8-bit number. So in which case the number of samples that are present in would be number of bits that would be present in one picture is 2 megabits. Now, if the speech is then converted, then if it is a colored signal, we need 3 colors to represent one color signal. We have red, green, blue component, or we have the intensity and the monochromatic and the color components. There are different versions of the color components. In any case, there are 3 components present, and if each one component, the intensity of each one of these components is converted to 8-bit numbers, then for each pixel we have RGB components. Then we need 8 bits for R component, 8 bits for green component, and 8 bits for blue component, in which case the total information will be into 3 per picture. Therefore, it would be this involves 6 megabits of information. Now, if well, these are the megabits per picture, 2 megabits per picture, and this is 6 megabits per picture. Now, if we have say 20 pictures per second, then we required here say 40 megabits per second of 40 Mbps, megabits per second information that is required to be transmitted. Whereas in this particular case, it is 40 into 3, it is 120 megabits per second. In fact, for conventional broadcasting purposes, we need a higher sampling rate that is required. Hence, the bit rate is much larger than this. For example, conventionally, the signal is first in the analog domain itself is scanned in the x direction first in this form, and then the next line and the next line, and so on. Therefore, we have an analog signal which represents the intensity in line 1, line 2, and so on. And when these are put together, it becomes a one-dimensional analog signal. Then, using a single sampler, the signal is sampled and then analog to digital converted. Now, in that case, the typical sampling rate that is used is of the order of 10 megahertz. In fact, 13.5 megahertz sampling rate is a standard. So let us consider say 10 megahertz sampling rate. Then we have a one-dimensional signal which is sampled at 10 megasamples per second. And now if each signal sample is converted into 8-bit number, then it becomes 10 into 8, it is 80 megahertz or megabits per second signal. Now if it is color, 80 into 3, it's a 240 megasamples per second. Is monochromatic signal. Therefore, the transmission rate is very high, of the order of 80, 240, 120 and 40 megabits per second. Sorry, this is megabits per second. Well, by digitizing the signal, we have some advantages. So these advantages are as given here. We have flexibility in handling. In processing and handling. We can, once the signal is converted into a sequence of numbers, these numbers can be stored in any memory. So they can be handled easily, they can be transmitted from a digital memory to another memory. And similarly, processing becomes easier because we have numbers to deal with, and once you have numbers in hand, or with the help of a computer, these numbers can be, any kind of processing can be applied on these numbers using digital hardware or in CPUs in a very accurate and an easy form, easy manner. Then encryption is possible. We can encrypt the signals. For example, once we have sequence of numbers that are available, then they can be jumbled up in a known form and transmitted to the destination, and there it can be reconverted into the original form. So this is possible in a much better and easier way for digital signals than for the analog signals. Then we have digital signal processors and hardware made using digital signal processors available. So these are used for number crunching, and they can do the processing at a very fast rate. And the signals can be processed using the DSP hardware. Well, for applying DSP hardware, the signals are to be digital signals, whereas in the case of analog signals, we have to go for analog signal processing techniques, which have several limitations in, like the dynamic range, accuracy, and so on. Then multiplexing of signals is possible. For instance, in multimedia, we need to multiplex the different media like picture signals, audio signals, and data. And since we have numbers to deal with, we can multiplex the numbers in time and then transmit them in an easier way than for the analog signals. Well, the coding is basically for coding of signals, as I mentioned, is basically used for the transmission applications over communication media, or transmission over communication media, and for storage purposes. Storage like storage on CDs, storage on tapes, and the transmission includes the conventional media as well as the computer networks. Now for these applications, why do we do coding? So coding is basically done for first in the primary form to convert them into number form, and in most of the advanced systems coding is done for compression. To compress the signal into a reduced form. As we have seen earlier, the digital signals involve high bit rates of the order of 80 megabits per second, 240 megabits per second for picture signals, and for signals like speech, it is 8 kilosamples per second into 8 bits per each sample is 64 kilobits per second, and similarly for audio it requires sampling of the bit rates of the order of hundreds of megabits per second, like 700 megabits per second and so on. Now these transmission rates, which I said like 64 kbps for speech, telephone speech, of the order of 700 kbps for audio, and 80 to about 240 megabits per second for video. So these rates are very high rates, and for transmitting such signals we need a large bandwidth, channel bandwidth. For instance, for transmitting this signal we require a channel bandwidth almost of the order of the same order as 240 megahertz. That means a satellite transponder the entire satellite broadcasting bandwidth of 500 kilohertz can only be used for only transmitting 2 video signals. Similarly, we have speech signals, a lot of speech signals in the trunk traffic, and to transmit them in the same form it consumes a huge bandwidth. Therefore, we need to compress the signals. And if this is the order of the speech, the pictured signals, then a CD can be used only to store information over a fraction of a minute. So then you can't use a CD for applications like picture applications, and at the most it can be used for only storing short clippings. So therefore we need to compress these signals if compression is permissible. Well, these signals have a lot of redundancy in them, and hence compression is possible, and the picture signals are compressed using different techniques to a very low bit rate, and these are then used for transmission and for storage. Therefore, at the other end you have to decompress the signals using a decoding technique and get back the signal. Now the compression methods need to be standardized, otherwise the different companies go for different compressing hardware, and you cannot use them with any other company's hardware. Hence we have different standardization organizations available to standardize the different aspects of the global communications. We have organizations like International Telecommunication Union. It's as an international body under United Nations organization. It has two different units, CCITT, Telephone and International Telephone and Telegraphic Consultative Committee, and CCIR, International Consultative Committee for Radio. As the name indicates, this is for telephone standardization, this is for radio standardization. We have International Standards Organization, ISO, American Telephone and Telegraphic Company AT&T, American National Standards Institute ANSI, and European Telecommunication Standardization Institute ETSI, and IEEE is another large body which also takes up the standardization job. So we have different standardization organizations which have standardized the video and audio compression methods, and we have a few standards available. In many cases, so these organizations work hand in hand with other organizations and then produce these standards. For speech compression, we have different standards available. We have normal pulse code modulation standard, which doesn't involve any form of compression, but it only involves the digitization part. So this standard produces 64 kbps speech, and this is used for the conventional digital telephony. We have adaptive differential PCM standard, which uses some form of compression, and the typical bit rate is 32 kbps, which is also a telephone communication standard, and it is also being adopted for the third generation wireless communications. We have different forms of linear predictive coding standards, and these are in the form of RPE LTP, regular pulse excited long term prediction compression standard, which compresses the speech bandwidth from 64 kbps to 13 kbps, and it is used for mobile communications in Europe and India. And since the wireless bandwidth is more expensive, we need to go for a higher and higher compression rate, hence these are used. Similarly, we have vector sum excited linear predictive coding of speech. This is used in United States for their mobile communications, and the speech bit rate is compressed to about 8, or strictly speaking 7.9 kbps. And we have a few variations of this, and we have pure LPC also, so which produces synthetic quality speech, and there is a standard 2.4 kbps LPC speech standard that is available, and this is used for defense communication, some important defense communications in the US. As I mentioned, this standard is used for global system for mobile communications, GSM standard for mobile communication, which is used in Europe and India. Similarly, we have different standards for the picture signals also. The normal PCM, as I mentioned, which doesn't involve any compression except for digitization, and as you have seen, the bit rates are of the order of 80 megabits per second for monochromatic, and then about 240 megabits per second in the case of picture signals, the color signals. Then we have ADPCM standard for picture. Then we have all modern standards like the JPEG standard for still pictures, Joint Photographic Experts Group standard for still pictures. Its compression abilities of the order of 10 to 15. That means the bit rate can be reduced by a hopping rate of 10 to 15 times. Then we have the H.261, H.262, the H series, H.263. The 261 and 263 are all our CCID standards. So these are meant for transmission of speech at multiples of 64, transmission of pictures at multiples of 64 kilobits per second, like 64, 128, and so on. Please note that the bandwidth is very low. It is only possible with highly reduced frame rate and reduced number of pixels in the x and y directions, whereas 262 is used for broadcasting purposes. Then we have moving pictures experts group MPEG. It has its MPEG 1, 2, 4 and few others like MPEG 7 and so on. So this is used for CD storage of video, and this is used for digital video broadcasting and digital video distribution. That means for broadcasting quality video, and this is used for again for network speech, and then for very low bitrate channels like telephone channels like H.261 and 263. Now the picture and speech compression, speech and audio compression techniques are used in various applications, as I have already mentioned in between during the course of this lecture. It can be used for telephony. It can be used for storing the signals like audio or video CDs, audio or video digital audio tapes and video tapes. Then it can be used for mobile communications, and it can be used for producing network speech like internet speech and voice mailing. Then it can be used for digital picture transmission and also for digital picture telephony and multimedia applications, which involve a combination of these. And we shall discuss further about it in the next class.